Now, I want to use this suggestion that we can now calculate a property to jump into NMR spectroscopy, because the reality is that most molecules that we're going to calculate a spectrum on, or an NMR spectrum on, are going to be flexible. And when we were talking about little tiny molecules, we could begin to say that everything is rigid or very few conformers. But when you start getting into the realm of the organic realm of 50, 100 atoms, things are flexible. So if I want to begin to talk about spectroscopy, I really have to be able to encompass flexible as well as rigid molecules. Everything I'm going to say from now on is going to mix these two. I'm really going to ignore conformation because I'm simply going to mix it in. So every time I think about a flexible molecule, I'm actually going to be using these Boltzmann weighting techniques. The NMR spectrum is very simple theoretically. It's an energy change, which is the excitation between nuclear spin states. It's essentially proportional to the strength of the magnetic field at the nucleus. Okay, you know all this. So the only thing I have to be able to calculate is the magnetic field strength at the nucleus. That's it. That turns out to be fairly simple. It took a long time for people to recognize that it was simple, but NMR is actually, of the spectroscopies that we can deal with, which are infrared Raman and ultraviolet visible, NMR is actually the least costly of the bunch. It turns out that there have been very good NMR calculations on very small molecules. There have been a couple cluster calculations. These are extraordinarily expensive. But they're valuable in the sense that they're telling you what the limit of the theory is, or they're telling you perhaps what the limit of precision of the experiments are. So how close can I actually get comparisons that are meaningful? There is a set of maybe 50 molecules, I don't know how many points there are, and these are experimental chemical ships. These are all pretty small molecules, so some of the experimental data are strange with regard to how do you do a gas in an NMR. And you can see there's a fairly good correlation. There's one blaring exception. It's carbon tetrachloride. I have no idea why it's an exception. But if you look at this set of molecules, it's about 50, I think. The mean deviation is something like 3.5 ppm. If you remove carbon tet, it goes way down to about 3 ppm. That's getting close to what I would consider a useful range in NMR. I'll talk about that in a second. It's probably not there yet. This is over a huge range. This is over a range of less than 0 to 225, so it's over a big range. If I ask a slightly better question, instead of looking at all these diverse molecules, I simply focus on one kind. So I'm going to focus on the few sp2 carbons in the set, the ethylene, imidazole, and these are in the set. There are only 6 molecules that have sp2 carbons in the set. And they have a range smaller, 110 to 160 ppm. What you see now is that the error in that set is something like 2.2. That is actually getting close to useful. Now, the problem with this is that this kind of calculation, couple cluster theory, and anything even of the size of benzene, is really extraordinarily costly. So you really can't do this in a routine way. So you have to look for simpler things. I'm going to take the following approach and ask the following question. I'm going to start with a method. It's either going to be Hartree-Fock or in reality it's going to be density functional. I'm going to start with the simplest possible basis that I can get away with and gradually build it up. I'm going to go from 631 star, which is a double split and a D function on heavy atoms, to 631 double star, which is the same thing with a polarization on hydrogen as well. I'm going to go in that direction. Then I'm going to go in this direction, which goes a double split to a triple split with one D function, two D functions on both hydrogen and carbon, forgive the giant asterisk, to one more step, which is the same thing, but now two sets of D functions, so I'm going to gradually go complex in one dimension, complex in another dimension, and then more complex. And ask the question, does it make any difference? And if you pick the best one of these combinations, which presumably should be this one, is it good enough? I want to make sure I'm targeting molecules that are at least molecular weight 500 to 800. I don't want to be targeting molecules that are molecular weight 100. Okay, so I want to get into organic molecules. If you look at this, I'm going to give you two sets of data, and they're going to be a little bit strange. I'm going to pick one molecule strychnine, just a typical rigid molecule. Here I don't want to worry about conformation. And I'm just picking 5 carbons, sort of diverse. And I'm going to look at, this is the B3LYP functional, and I'm going to look at the chemical shifts experimentally at those points and then calculate them. And I want you to make 2 observations. The first observation is that as I go from adding polarization on only carbon to adding polarization on hydrogen, it doesn't make any difference. These 2 columns are almost identical. These 2 columns are almost identical. I'm doing the same thing. So the first observation, and it's reasonable because I'm talking about carbon shifts. Changing hydrogen, it doesn't do much. If I were talking about proton shifts, it might do something. The second observation is that this set, either one here or either one here, are different. So adding a second, splitting the valence from a double split to a triple split is actually important. Going from either one of these to adding the second set of polarization, that's this column versus this, is really not important. So the first observation is that one kind of change in the base set is not important, adding functions to hydrogen, which greatly increases cost because there are a lot of hydrogens. The second observation is going from splitting twice to splitting 3 times does change. Okay, what is more important is if you look at the experiment, neither of them are very good. This is the best one here is sort of terrible, but you have a good match here to here, but you have a bad match here to here. So the conclusion for this one functional, the old functional B3LYP, is that of the 5 choices I've done, really none of them are very good, and it doesn't make much difference which one you choose. The same conclusion applies if I use this on the XD functional, which is the one I'm going to finally play with. Again, you see no change between adding functions on hydrogen here or here. You see a big change between having 2 valence and 3 valence. None of them are really any better than any of the others. So we're left with the conclusion, on this simple molecule, we're left with the conclusion that the limits of the theory are really no better than earlier variations. Okay, here I'm going to take just one of them. The one I'm going to take is this one here, which is the simplest one. Okay, I'm going to use that functional. I'm going to take the simplest one, and I'm going to put a plot. So this is now experiment versus the simplest of the calculations. So this is a calculation that can be done on a big molecule. In the aliphatic region, sp cubed carbons, we have a correlation line which is that. It's not perfect. You're seeing errors of a few, but there's probably not a systematic error. In the olefinic region, aromatic olefinic, it's mainly olefinic. I've tried to not use very many aromatics. There's clearly a systematic error. You're clearly shifting down by several ppm. But you also have a random error, just like you had here. Okay, so we're seeing that in graphical form. You could do this for a huge number of molecules and you see the same thing. If you look at the statistics, what you see is that the errors are roughly 5 ppm. This is carbon shifts. And this is true for every functional we've tried B3 lip, we've tried EDF2, which was our standard a few years ago, we've tried this, we've tried better ones. You can't really get below about 5 ppm. The comment I would make is that this is too large to be useful. 5 ppm, if you're trying to distinguish between stereoisomers, is just too large. You have to knock this down by a factor of 2 or 3 to become useful. The way that we've chosen to do this is to empirically correct, and we've developed over the years 3 generations of corrections. The current version of Spartan incorporates the last one. And what we've essentially done is to start with the calculated one, that's the lead term, and then introduce a term that looks at the neighbors. It distinguishes between 3 kinds of carbons, sp, sp cubed, and sp squared, and then looks at the neighbors and writes a power series expansion for every different kind of neighbor in the bond length. You could also use bond orders, it doesn't make any difference. What this results in is about a 50 parameter fit based on about 2,000 very clean experimental shifts. What's critical is to get very constant experimental data here, and we've done that. I should remind you that 50 sounds like a big number. Some of the functionals we've been using, the TrueLAR functionals, have 40 parameters, so parameterization is not uncommon. When you do that, the best of the fits, which is this one, give a mean error of something like 1.6 ppm, about 3 times better than the uncorrected one. The worst of the fits, which is B3 lip, is about 1.8. They're not very different. We've repeated this for several basis sets, several permutations of that. I'm now going to use a single method from now on. I'm going to be using this method with this basis set. That's the one I've chosen to sort of look at rather carefully. I don't think it makes any difference, actually. How good is 1.8 ppm? Here's a tiny molecule, nicotine. It's the biggest thing I could fit in a table. If you look at this, the experiment and the calculator, very good. I mean, you will see differences of 2 ppm because we're going for a mean of 1.6. So you'll see some that are perfect. This is the sort of quality you can expect where confirmation is not a problem. It's actually not in this case. If you look at something more complicated but also rigid strychnine, what I'm plotting here is the mean difference in chemical shifts over the molecule. And you can see we have a couple that are 2. Typically, you're sort of lower than 1. You're 1 or lower. So that's what difference is. Now, I would contend that this is getting to be useful, and I'm going to show you that in the last few slides of this section by looking at. I'm asking a somewhat different question. Okay, if you think about an experiment versus a calculation of a spectrum, and NMR is a good case. The experiment is an exact spectrum. Once you've filtered all the junk out, the solvent and what have you, that spectrum is exact. You try to deduce from that spectrum the structure. That's the purpose of most NMR experiments. So you have an exact spectrum and you're trying to guess the structure. The theory is exactly the opposite. You have an exact structure. That's what you're starting with. You may have flexibility, but let's not worry about that. And you're calculating an approximate spectrum. So the two are complementary to each other. Exact spectrum, guessing the structure, exact structure, guessing the spectrum. More than guessing, approximating it. With that in mind, you can think of 4 possible uses for calculations in conjunction with experiment. The simplest and probably most common, but not most important, is that you can take a spectrum where you know what the structure is. There's no certainty, and you can assign it. You can assign this absorption goes to this carbon, or hydrogen for that matter. So assignment is one thing. The second thing you can do, which is, I think, far more important, is you can say, here is a proposed structure. You can say if that structure is consistent with the calculated spectrum. You can't say it is exact, but you can say it is either consistent with or wrong. You can say, here's an experimental spectrum. The spectrum is not questioned. Here's my structure assignment. I can say that it's either reasonable or wrong. Okay, and there's a fuzzy boundary. Associated with that, you can choose among several structures that are most consistent. So you can say, here are 5 possible structures. This one is more consistent with the calculation than this one, and these are wrong. Okay. The last thing, and I think an unrealistic goal at this stage, is you can actually suggest what the structure is. This is really something that I think is beyond, this is a databasing problem. Let's look at the first one. Here's a very simple example. It's the molecule's chemazuline. If you look in the reported spectrum, the spectrum is fine, the structure is fine, the assignment is wrong. The assignment between that carbon and that carbon are inverted. Okay, that's not terribly exciting, but it's very common. Misassignments of this nature are very common. Here's the second thing where the structure is uncertain. I'll pick an example where I didn't do the work, someone else did. Here's the original drug. It's a natural product. The original assignment is that. The reassignment, which was based on synthesis, is that. If you look at the calculations of the 2 structures, here is the experimental spectrum, which is exact. Here's the original assignment. If you look down this carefully, you'll see that it's terrible. You have some very large variations. Let me find one of them that are completely off base. There's one that's off by 10 ppm. Remember, our mean error is about 1.6. That means that the standard deviation is about 1.7, 1.8. That means that 2 standard deviations is 95%. By the time you get to 3 standard deviations, you're 1% probability that you're right. So that's 6 ppm. So we have a deviation of 10. There's something wrong. When you look at the reassigned structure, it's pretty good. It's not perfect. I mean, we have a deviation of 3, deviation of a few. But you can see that this assignment, if I were given 2 choices, I would clearly pick that one over that one. I have to be completely honest. The calculations can't rule out a structure that was proposed, but they can say that one is clearly better, more consistent with the theory, with the calculations than the other. All right, now this leads me, let me just touch on other nuclei for a second, then I'm going to go to my final topics. Chemical shifts, from the perspective of the calculation, I don't care what the nucleus is. Obviously, if it's spin, if there's no spin, then the shifts will come out 0. But of the finite ones, whether you're proton or F19 or phosphorus, everything falls out of the calculation. We've carefully worried about proton and also about fluorine. We've done the same kinds of empirical corrections for those. They're both much simpler because you don't have the variety of bonding environments, but we've done the same kind of correction schemes for that. And here's an example of a corrected one. I'll go back to chemazuline again. These are experimental shifts versus calculated ones, and they're essentially very good actually. Now, I bring this up because I want to discuss one more thing. I put the 3-bond coupling constants in parentheses. These have actually been determined empirically. Very recently, we've brought in the ability to actually calculate coupling constants. I'm not sure it's worth much. If I look at a set of, this is about 100 molecules, I think. If I look at experimental coupling constants versus empirical ones that we simply get from a modified Karplus kind of equation, just based on geometry. If I look at that, the correlation is actually pretty good. If you consider that coupling constants are really, the experimental importance is to not distinguish things that are 1 hertz apart, but things that distinguish things at the 3 or 4 hertz, arrangements that way versus that way. This is actually quite satisfactory. We can now calculate coupling constants if we want, and if you do that, this is using only one of the terms in the expression for the coupling constant. It's the important one, which is the so-called Fermi contact term. If you take the same set, this is the same set of molecules, and you now calculate, it's actually pretty good. This calculation is about 5 times more costly than the chemical shift calculation. I'm not sure that it's worth doing. However, what the empirical calculation, what the Karplus calculation is doing is really 3-bond coupling. There is no equivalent for longer range coupling empirically. There's no conspicuous relationship. We and others have played with this. But once you calculate a coupling constant, you get everything. And so here is higher order 4 and 5 bond coupling. There are not that many really good experimental data that are easily extracted, but when you do extract it, you actually get small numbers. These are less than a few hertz, so they're a third of the range of 3 bond coupling. And you see a reasonable correlation. There are 2 correlation lines. I would love to say these are 4 bonded, these are 5, but it doesn't work out that way. So there's something not clear here. The reason I bring this up is that whether you establish coupling constants by empirical methods or by actually calculating them, you now have the fundamental information to produce many different variations of NMR spectra. In other words, the 2D spectra. So given the calculated data, again, whether or not coupling constants are calculated or empirical, you can now do things like cozy spectra, a lot of the common 2D spectra. You can also do depth spectra, which has nothing to do with coupling constants. Let me just show you examples. For example, you can take some object and you can do a depth spectrum. We're not doing a different experiment. We're simply saying, I know what kind of carbon yet. So simply writing the lines differently. In the case of 2D spectra, they don't exactly look like what you measure experimentally because the experimental ones have all sorts of variations due to you're playing different conformations, you're averaging. We're not doing that. But you can actually develop lots of different permutations that experimentally would be different experiments. I want to lead into larger molecules. I've been talking about small molecules. And I always want to make one comment about conformation. NMR shifts do depend on conformation. I give a very pretty example here. This is a molecule called Johnsonol, and if you look at this in a drawing, it looks pretty rigid. It's hard to flex a ring that's fused. However, this molecule has 2 conformers that are almost the same in energy. Those 2 conformers are the chair and a boat. This is one of the few examples that I've been able to find where actually the boat is slightly favored. And the reason is that the chair forces the 2 halogens axially. The boat actually puts them equatorially. So you're competing between 2 preferred arrangements. I'd much prefer things to be equatorial, but I'd much prefer things to be chair. And it turns out that competition produces something that is actually quite close in energy to each other. If you look at there's one experimental spectrum. If you look at the twist boat versus the chair, you'll see the experimental spectrum almost always falls just about in between. So we're actually averaging the two. Now, this is going to lead into a more serious, stringent test of the methods. I'm going to pick one method again, and I'm going to look at carbon spectra of a variety of natural products. And these are going to range from, there are a couple of tiny ones around 200, and there are a few very large ones, in my world, large around 700 or 800. I'm going to consider mixing both rigid, very few of them are rigid, and flexible molecules. And the flexible molecules are going to use the recipe that I described an hour ago, where the final Boltzmann weight is going to be based on that model. Okay? So these are calculations that are not single molecules. There are as many as starting from several thousand and landing up with, I think the biggest one lands up with 30 that are less than 10 kilojoules. Okay, I'm going to divide this very purposely into two sets. The first set is about 300 molecules for which there are X-ray crystal structures. What that tells me is that the structure assignment is correct. So I know what the structure is. There may be one or two exceptions in there where the crystal structure can be wrong, actually. But let's assume no. So I've got 300 molecules. There are about 5,500 carbons. So it's a big set. And the structure is correct. The line assignments may be different there, so that may be some of the problems associated here. If you look at this, I'm going to look at the individual carbons. And what you see is you have a nice distribution. That's important, because what that tells you is that there is no very giant systematic error. If this were really skewed to one side or the other, it's a little bit skewed to the right. But if this were skewed a lot, this would tell you you've got a systematic problem and you've got to go back and reparameterize. The fact that it's uniform means my parameterization set is representative of these molecules. This is a much bigger set than I used to parameterize. About 90% of the shifts are within 3 ppm. There are a few there's one that's 9. That is probably misassignment of a line switch. I'm not worried about that so much. But there are about 2% that have errors in excess of 5 ppm. What this tells you is what you can expect of correctly assigned structure. Okay, I put the data in a different form. This is looking at a molecule basis, and it's saying what is the largest, what is the RMS error. So it's RMS is picking on the larger deviations, and so if you look at RMS error, you're seeing that essentially there are a few molecules that are 3.5. That's what this bar is. Most of them are between 1.5 and 2.5 ppm as RMS error. So this says what you can expect. So this is a confidence builder. What are the errors? Well, there are many sources of errors. One is that the theory itself has got an inherent error. Second is that the Boltzmann weights are not great, and they may be poor because of solvent. Solvent not only changes the shift, it also changes the Boltzmann weight. Preference of one conformer in one kind of solvent may be quite different from another kind of solvent. There's not enough data to actually know that. The other source of error may be the shift itself depends on solvent. Now, one has looked at that by doing the following exercise. If you take that set of 300 molecules and you now separate them into two classes, those that are done in one solvent, and chloroform is the dominant one, versus ones that are done in all solvents. So this is a subset. What you see is that this is a tighter distribution. If you look at that, now skip back to that this is the molecule distribution. This distribution And we have half the number of molecules, so this distribution is tighter. Not by much, maybe 20%. So this suggests that there's a small dependence of the shift itself on solvent. Again, there's not enough data to detect. Now, the important thing in this is that this is a calibration. This says, what can I expect? Let me now look at a second set. The second set is different from the first. It's a different set of molecules. They're about the same size, and there are about 350 of them, of which there are about 5,500 unique carbons. So that was chosen to have the number of carbons about the same. But these are molecules where there is no crystal structure, and you might want to challenge the experimental assignment. It's not as clear, okay? It's always amazed me how good they are. If you look at this plot, and I'll do the atomic plot first, you see the curve is, again, nicely symmetrical. It's clean. But you now see, before we had almost no outliers past 5. Here you see outliers that go further. The big bar at 10 is everything 10 and beyond. And so here you see clearly there are more outliers. This is more clearly done by showing it over atoms. The set where there were crystal structures basically flattened out at this number right here, 3.5. There was really nothing past that. Here you see there are a lot of things past that. You can forgive maybe these. You can't forgive these. These are wrong structures. I don't want to pick on the experiment, but this is a way of filtering out at a very early stage things that are wrong. Let me put that data in a different form. This is the two sets of molecules. They're about the same size, so I can put them on the same scale. The blue line is crystal structures, and what this tells you is that at 3 ppm, we're about 90%. So 90% of them are inside 3 ppm. By the time we get to 4 ppm, we're about 98%. And so it's 3 and 4. When you look at these are ones with crystal structures. Without the crystal structures, we're about 80% at 3 ppm and only 90. So we've gone down by about 10%. What this tells me is that 10% of that second set are problematic. My suggestion here is that the computational technique is a great filter. At the point where there is an NMR spectrum and a proposed structure, it's a great filter to really say that proposed structure is either reasonable or it's wrong.